Right now, as you listen to this, a signal is traveling through interstellar space toward Earth. It left its source approximately 22 hours ago. It is traveling at the speed of light, 186,000 miles per second, and it is crossing a distance so vast that even at that speed, the journey takes nearly a full day. When it arrives, it will be received by an antenna somewhere on Earth, processed by instruments built specifically to detect it, and translated into data by engineers who have been doing this work for nearly 50 years. The signal is extraordinarily faint. By the time it reaches us, it carries less power than a single snowflake falling on the ground. It is, by almost every measure, the weakest signal that human technology currently detects on a routine basis. And yet, it is detected, every day, without fail. The source of the signal is a spacecraft called Voyager 1. It was launched on September 5, 1977, 47 years ago. It weighs roughly 722 kilograms. It is powered by the slow decay of plutonium-238, a process that has been running continuously for nearly 5 decades, providing a small but steady trickle of electricity to the instruments and transmitters that keep it alive. Its onboard computers have less processing power than a modern digital watch. Its memory is measured in units that would seem laughable on any device you own. And it is currently 24 billion kilometers from Earth. That number, 24 billion, is not one that scales easily. If you drove a car at highway speed, continuously, without stopping, it would take you roughly 26 million years to cover that distance. If you could somehow watch Voyager 1 from Earth with a perfect telescope, the light you would see leaving it right now left 22 hours ago. You would not be seeing Voyager as it is. You would be seeing Voyager as it was yesterday. It is the most distant object humanity has ever made. It has crossed the boundary of the solar system and entered interstellar space, the vast, cold, essentially empty region between the stars. It travels through a place where no human being has ever been, where no human being will go in any lifetime currently being lived, where the sun is just another star in a sky full of stars. And it is still going, still transmitting, still functioning, still sending that faint signal home across 22 hours of empty space, carrying data from instruments that are measuring the environment of a region of the universe that nothing built by human hands had ever reached before Voyager 1 arrived there. But what that signal contains, and what Voyager 1 is carrying with it into the dark, is what makes this story unlike any other in the history of human exploration. Because Voyager 1 is not just a scientific instrument. It is something else. Something that becomes clearer the longer you think about it. Something that sits at the intersection of science and philosophy and a very particular kind of human feeling that doesn't have a clean name. It is the loneliest object in the universe. And it was made by us. To understand what Voyager 1 is, it helps to spend a moment with what it isn't. It is not large. Parked next to a school bus, it would look modest. Its main body is roughly the size of a compact car. Extending from that body are instrument booms, long arms carrying scientific sensors, and a large dish antenna, 3.7 meters in diameter, which is the ear and mouth through which Voyager communicates with Earth. The antenna is always pointed at home. In 47 years, it has never looked away. It carries 11 scientific instruments, most of which were designed to measure phenomena that hadn't been directly measured before Voyager made it possible to measure them. Magnetic fields, plasma, the ionized gas that flows through the solar system and, it turned out, far beyond it. Cosmic rays, radio waves, the properties of the interstellar medium, the thin, cold material that fills the space between stars. It runs on 3 radioisotope thermoelectric generators, devices that convert the heat from radioactive decay directly into electricity. There is no solar power. At Voyager's distance from the sun, sunlight is so weak that solar panels would be essentially useless. The plutonium does the work slowly and reliably, its power output declining by a small fraction each year as the radioactive material decays. The computers on board are, by modern standards, extraordinarily primitive. They were state-of-the-art in 1977. Today, they are relics. The programming language they run is one that essentially no one uses anymore. When engineers at NASA's Jet Propulsion Laboratory need to send commands to Voyager, they work in systems and languages that are decades out of date, maintained specifically because there is no alternative. You cannot simply update Voyager's operating system. The spacecraft is 24 billion kilometers away, and the code that runs it is frozen in time. And yet it works. Every day, the instruments measure. Every day, the data is compiled and transmitted. Every day, the signal makes its 22-hour journey across the void, arrives at Earth, and tells the engineers that Voyager 1 is still there, still functioning, still alive in every meaningful sense that can be applied to a machine. There are people at JPL who have worked on the Voyager mission for their entire careers. Scientists who were young when Voyager launched and are now in their 70s and 80s, still receiving data from a spacecraft they helped design before some of the people reading about it were born. There is a continuity to this story, a thread of human attention and care that has stretched unbroken for nearly 5 decades, across the farthest distance any human artifact has ever traveled. Voyager 1 has no crew. No living thing has ever been on it. No human hand has touched it since it left Earth. And yet there is something undeniably alive about the relationship between this machine and the people who built it, launched it, and have been listening to it every day since. It is out there, and we are still paying attention. And yet it is doing something no human being has ever done. It is traveling through interstellar space, the space between the stars, and sending back measurements of a region of the universe that was, before Voyager arrived, completely unknown to direct observation. No probe, no telescope, no instrument had ever sampled the interstellar medium from the inside. Voyager 1 is doing that right now in real time as you listen to this. But to understand why that matters, and why this machine carries something far more significant than scientific instruments, you need to go back to 1977. To a moment when a group of scientists sat down to ask a question that had never seriously been asked before. If this spacecraft travels beyond the solar system and is eventually found by something that didn't build it, what should it carry? The year 1977 sits at an interesting place in human history. The first personal computers were just appearing. The internet did not exist. Mobile phones did not exist. The most powerful computers on Earth filled entire rooms and were operated by specialists who communicated with them through punch cards and command terminals. The idea that a person might one day carry in their pocket a device more powerful than all of those computers combined was not science fiction. It simply had not occurred to most people. And in that world, the engineers and scientists at NASA's Jet Propulsion Laboratory in Pasadena, California, were preparing to launch 2 spacecraft that they knew would eventually leave the solar system entirely, that they knew, in all probability, would outlast human civilization, that they built with this knowledge and designed accordingly. Voyager 2 launched first on August 20th, 1977. Voyager 1 followed 16 days later on September 5th. Despite the naming, Voyager 1 was designed to travel faster and on a different trajectory. It overtook Voyager 2 and has remained farther from Earth ever since. The launch window for both spacecraft was extraordinarily specific. It exploited a rare alignment of the outer planets, Jupiter, Saturn, Uranus, and Neptune, that occurs only once every 175 years. In this alignment, a spacecraft could use the gravitational field of each planet as a slingshot, gaining speed and changing direction to reach the next planet, without carrying the enormous quantity of fuel that direct travel would require. The alignment in 1977 was, in a very real sense, a one-time opportunity for a generation of scientists. Miss it, and the next chance would come in the mid-22nd century, long after everyone involved would be gone. They did not miss it. The team that designed and built the Voyager spacecraft was led by Edward Stone, a physicist who would serve as the mission's chief scientist for decades. Stone was meticulous, patient, and deeply committed to the scientific value of what Voyager might find. He understood, perhaps better than anyone, that the spacecraft they were sending out were not just scientific instruments. They were a kind of permanent record, a physical presence in the universe that would outlast everything built before or since. The night of Voyager 1's launch, September 5th, 1977, was clear at Cape Canaveral. The spacecraft rode a Titan IIE rocket into the sky, small and silver, disappearing quickly into the dark above the Florida coast. The people who had built it and the people who would spend their careers listening to it watched it go. Many of them knew, even then, that they might never see the most important data it would send. That Voyager's journey into interstellar space, the destination that would prove most scientifically significant, would take decades. That the measurements from interstellar space would come to scientists who were, in 1977, still in high school, or not yet born. They launched it anyway, for the future, for science, for whoever came after, and for one more reason, one that was not originally planned as part of the mission, but that became, in retrospect, perhaps the most important thing Voyager 1 carries. In early 1977, with the Voyager spacecraft already in the final stages of construction and the launch window approaching, a scientist named Carl Sagan received a phone call. NASA wanted to include a message on the Voyager spacecraft, a physical artifact designed to communicate something about humanity to whatever might eventually find the probe in the depths of interstellar space. The agency had done something similar before. Pioneer 10 and Pioneer 11, earlier spacecraft that would also eventually leave the solar system, had carried small gold anodized aluminum plaques bearing simple diagrams of a man and a woman, a representation of the solar system, and a map showing Earth's location relative to nearby pulsars. But for Voyager, NASA wanted something more ambitious, and they turned to Carl Sagan. Sagan was already one of the most famous scientists in the world, an astronomer and cosmologist whose ability to communicate the wonder of the universe to a general audience was unmatched. He was also deeply invested in the idea of communication across cosmic distances, the possibility of contact between intelligent species separated by the vastness of space. He assembled a small team and began work on what would become the Voyager Golden Record. It is literally a record, a 12-inch gold-plated copper disc, enclosed in a protective aluminum jacket. On the outside of the jacket are instructions, drawn in diagrams rather than language, since no known language could be assumed to be readable, explaining how to play the record, how to interpret the images encoded on it, and how to locate Earth in the galaxy using the signals of pulsars as reference points. What the record contains is one of the most extraordinary artifacts ever created by human beings. There are 115 images, encoded as analog signals on the record's surface, photographs of Earth, of life, of human beings. Images of a man and a woman, of a nursing mother, of children, of people eating and running and working. Images of forests and oceans and deserts and cities. Images of DNA, of cells, of anatomy. Images of the solar system. Images taken from space, showing the Earth as a small, bright sphere against the black of the void. There are sounds. The sound of wind, rain, thunder, surf breaking on a beach. The sounds of animals, birds, whales, a chimpanzee. The sounds of a human heartbeat, footsteps, laughter, a mother's first words to her newborn child. There are greetings in 55 human languages. Brief messages, a few words each, saying hello in forms as different as Akkadian, a language spoken 4,000 years ago in ancient Mesopotamia, and Mandarin and English and dozens of others. A child's voice saying, in English, hello from the children of planet Earth. And there is music. 90 minutes of music from across human history and human geography. Bach, Beethoven, Chuck Berry's Johnny B. Good, a Navajo night chant, Azerbaijani bagpipes, a Pygmy girl's initiation song, Peruvian wedding song, the flowing streams of Chinese Guqin, Blind Willie Johnson playing Dark Was the Night, Cold Was the Ground, a wordless, mournful slide guitar piece recorded in 1927 that Sagan described as one of the most moving pieces of music ever recorded, an expression of human loneliness and hope that needed no translation. The record was assembled in 6 weeks. Working against the deadline of the launch, Sagan's team made decisions about what humanity was, what humanity felt, what humanity wanted an unknown finder to understand. Every choice was a statement about what we consider worth preserving, worth communicating, worth sending across the universe. Sagan later described the record as a message in a bottle cast into the cosmic ocean. He knew the chances of it being found were vanishingly small. The universe is almost incomprehensibly large, and Voyager 1 is almost incomprehensibly small within it. The probability of any intelligence ever finding it, in the absence of knowing where to look, is so close to zero as to be functionally indistinguishable from it. And yet, the record is there. On a spacecraft currently traveling through interstellar space at 38,000 miles per hour, carrying the sounds of Earth into a silence that has never heard them, carrying Bach and thunder and a child's greeting into a darkness that may never receive them. Whoever finds it will know exactly where we are. They will have a map, encoded in the signals of pulsars that don't change across thousands of years, pointing to a small star in the outer arm of the Milky Way. They will know what we look like, what our world looks like, what our music sounds like, what we consider beautiful and significant and worth sharing. And they will know something else, something that the record communicates not in any of its encoded images or sounds, but simply by existing, by the fact that a species built a machine, sent it into the dark, and chose to put this on it. They will know that we hoped. Voyager 1's first major destination was Jupiter, the largest planet in the solar system, a world so vast that more than 1,300 Earths could fit inside it. A planet with no solid surface, just layers of gas growing denser and hotter the deeper you go, until at some point far below the visible cloud tops, the pressure is so extreme that hydrogen itself becomes a liquid metal, conducting electricity like a wire. Voyager 1 reached Jupiter in March 1979, 18 months after launch. By that point, it had already traveled farther from Earth than any human artifact before it. And what it sent back was unlike anything astronomers had expected. The cloud systems of Jupiter, glimpsed through Earth-based telescopes as colored bands and the famous Great Red Spot, resolved into something almost incomprehensibly complex up close. Storms the size of continents, jet streams moving at hundreds of miles per hour. The Great Red Spot, a storm that has persisted for at least 350 years, possibly much longer, revealed as a structured, layered system of rotating clouds with a calm center and violent edges, a weather system older than any government on Earth. But the clouds were not the most significant discovery. As Voyager 1 passed close to Jupiter, it turned its cameras toward the planet's moons. Jupiter has, we now know, dozens of moons, but 4 of them, the Galilean moons first observed by Galileo in 1610, were the primary targets. And what Voyager found on 2 of them rewrote the boundaries of what was thought possible. On Io, the innermost of the 4 large moons, Voyager's cameras captured something that no one had predicted with certainty before the flyby: active volcanoes. Enormous ones. Eruption plumes rising hundreds of kilometers above the surface, higher than the altitude at which commercial aircraft fly above Earth. The surface of Io was covered in sulfur compounds of every color: yellow, orange, red, white, brown, testament to the constant volcanic resurfacing of a world that is, geologically, the most active in the solar system. The volcanic activity is driven by tidal forces from Jupiter, the enormous gravitational field of the planet flexing and squeezing Io as it orbits, generating heat through friction in the moon's interior. And on Europa, the smooth, ice-covered moon that Voyager photographed in detail for the first time, the cameras revealed a surface unlike anything seen before, not cratered and ancient like most solid bodies in the solar system, but young and smooth, crisscrossed by long, dark lines that resembled nothing so much as the surface of a frozen sea. Ice that had cracked, shifted, and refrozen over and over, suggesting that something liquid might lie beneath. The implications of a liquid water ocean beneath Europa's ice were immediately understood by the scientists reviewing Voyager's data. Liquid water, even in the dark, even far from the sun, even beneath kilometers of ice, is the most important prerequisite for life as we understand it. If Europa has an ocean, and if that ocean has a source of chemical energy at its floor, then the question of whether life exists on Europa becomes a genuine scientific question rather than a philosophical speculation. We are still trying to answer it. But what Voyager found at Jupiter did something beyond the individual discoveries. It established a principle that has guided planetary science ever since. The solar system is far stranger, far more varied, and far more potentially hospitable to complexity than anyone had assumed before Voyager arrived to look. What it found next changed everything we thought we knew. Not just about the outer solar system, but about something much closer to home. From Jupiter, Voyager 1 continued outward towards Saturn. The journey took nearly 2 years. On November 12, 1980, it made its closest approach to the ringed planet, and what it found there was, once again, beyond expectation. Saturn's rings, visible from Earth as a flat, featureless band of light, resolved into something of almost impossible complexity. Thousands of individual ringlets, gaps, waves, and braided structures. Rings within rings, gaps carved by the gravitational influence of small moons orbiting within the ring system itself. The F-ring, a thin, narrow ring just outside the main ring system, appeared to be braided, twisted around itself in a structure that defied easy explanation and that took scientists years to fully understand. But it was Saturn's moon Titan that Voyager 1 had been sent specifically to examine. And Titan delivered. Titan is the second largest moon in the solar system. It is also the only moon with a substantial atmosphere, a thick, hazy, nitrogen-rich atmosphere that, before Voyager arrived, was poorly understood. What Voyager found was a moon shrouded in an impenetrable orange haze, a photochemical smog produced by complex organic chemistry in the upper atmosphere. The cameras could not see the surface. The atmosphere was too thick, but the instruments could measure, and what they measured was extraordinary. Titan's atmosphere contains many of the same organic molecules that are thought to have existed on early Earth, the chemical precursors to life, drifting in the air of a moon colder than any place on Earth, bathed in the weak orange light of a sun 4 times farther away than it appears from home. The decision to study Titan closely changed Voyager 1's trajectory. To approach Titan at the required angle, the spacecraft had to pass above Saturn's North Pole, a path that bent Voyager 1 out of the plane of the solar system, sending it upward and outward rather than continuing along the equatorial plane where the other outer planets lay. This ended Voyager 1's encounter with the planetary solar system. It would not visit Uranus or Neptune. Those were left to Voyager 2 on its own separate trajectory. Voyager 1 was now headed, directly and irreversibly, for the edge of the solar system and the space beyond. The scientists had known this would happen. It was part of the mission plan. Titan was worth it. But as Voyager 1 sailed upward and outward, growing smaller and more distant with every passing day, an idea began to form in the mind of one scientist that would produce, in a few years, the most remarkable photograph ever taken. Carl Sagan had a request, a strange one, almost sentimental. He wanted to turn Voyager 1's camera around. It took years of advocacy. The engineers were reluctant. Turning the camera toward the inner solar system meant pointing it toward the sun, which risked damaging the sensitive optics. The scientific value was questionable. There was nothing out there to discover, no new data to collect. It was, in practical terms, a photograph for philosophical reasons. Sagan insisted. He wanted a portrait of the solar system, all the planets photographed from the outside, from a vantage point no camera had ever occupied. He wanted people to see, with their own eyes, what the solar system looks like from the edge. On February 14, 1990, with Voyager 1 approximately 6 billion kilometers from the Sun, already past Neptune, already at the outer boundary of the planetary solar system, the cameras were turned. A series of 60 frames were taken over nearly 6 hours as the spacecraft rotated slowly to capture the 6 planets that were visible from its position. Earth appeared in one of those frames as a fraction of a single pixel, a point of light so small and dim that it was almost lost in the scattered light of the sun falling on the camera's optics. A mote of dust suspended in a sunbeam. Sagan later described what he saw in that image and what he believed it meant, in words that have been repeated countless times since. He talked about the rivers of blood spilled so that, in glory and triumph, the generals and emperors of history could become the momentary masters of a fraction of a dot. About the cruelties that people inflict on each other, about the misplaced sense of self-importance in the assumption that humanity has some privileged place in the universe. "Look again at that dot," he said. "That's here. That's home. That's us." The pale blue dot photograph did something no scientific measurement can do. It changed perspective. It held up a mirror to humanity at a distance of 6 billion kilometers and showed something that all the history books and all the philosophy and all the religion had been trying to show from the inside, often without success. We are small. Extraordinarily, almost absurdly small. Our wars and our politics and our certainties and our grievances all occur on a pixel. A single compressed point of light in a photograph taken by a spacecraft that was itself barely visible as a point of light from Earth. And that spacecraft, that point of light among points of light, was made by the people on the pixel. Built by human hands, launched by human ingenuity, carrying a golden record with human music on it, already traveling faster and farther than any human-made object in history. There is something in that image that is both humbling and, if you look at it long enough, quietly extraordinary. The smallness of the pale blue dot is also a measure of what the people on it have managed to do. They built something that could photograph them from 6 billion kilometers away. They built it with 1970s technology. They aimed it at Jupiter and Saturn and Titan and sent back images that changed science. And then they turned it around, pointed it at home, and chose to look. One photograph, taken by accident essentially, by a camera on a spacecraft that had already completed its primary mission, repurposed for a moment of philosophical reflection. That changed how humanity saw itself. And then Voyager 1 kept going. After the portrait of the solar system was taken, the cameras on Voyager 1 were powered down. There was nothing left to photograph. The spacecraft was heading into empty space, and in empty space there is nothing to see. The imaging systems drew power that was better used elsewhere, and so they were switched off. Voyager 1 sailed on in darkness. For the next 2 decades, the spacecraft continued outward, its instruments measuring the properties of the environment around it, the solar wind, the magnetic field, the density of charged particles, while the scientists at JPL tracked its slow progress toward the boundary of the solar system. That boundary, called the heliopause, is not a wall. It is not a line you could see or feel if you were somehow present there. It is the point at which the solar wind, the constant stream of charged particles flowing outward from the sun, can no longer push against the interstellar medium, the thin material that fills the space between stars. Beyond the heliopause, the sun's direct influence ends. The interstellar medium begins. You are, in any meaningful physical sense, no longer in the solar system. For years, scientists debated where the heliopause was and what it would look like when Voyager crossed it. They had theoretical models. They had predictions. But no instrument had ever measured the heliopause from the inside. No one knew exactly what crossing it would look like in the data. In 2012, after 35 years of travel, something changed in Voyager 1's measurements. The density of low-energy particles associated with the solar wind dropped sharply. The density of high-energy cosmic rays, particles coming from outside the solar system, increased sharply. The magnetic field shifted. Multiple instruments registered the change simultaneously, and the data was unambiguous. Voyager 1 had crossed the heliopause. On August 25, 2012, Voyager 1 became the first human-made object to enter interstellar space. It crossed a boundary that had existed since the solar system formed 4.6 billion years ago, that no probe had ever crossed, that no human being will cross in any foreseeable future. It went from inside to outside, from ours to not ours. Edward Stone, who had led the scientific team for 35 years by this point, described the moment as the beginning of a new era of exploration. Voyager had become an interstellar probe, not by design initially, but because it had been built well enough and lasted long enough to become one. The data from interstellar space was immediately surprising. The interstellar medium did not match the models exactly. The magnetic field orientation was different from what was expected. The density of interstellar plasma was higher than predicted. Every discrepancy was a new piece of information, a new constraint on theories about the structure of the space between stars that could not have been obtained any other way. Voyager 1 was doing exactly what it had always done, finding things that were not quite what anyone expected, revising the picture, pushing science forward. It crossed a boundary no human object had ever crossed before, and then it kept going. But in 2023, something happened that no one was prepared for. Something that brought the entire mission, and the people who had dedicated their lives to it, to the edge of losing everything. In late 2023, the engineers at JPL noticed something wrong with the data coming from Voyager 1. It wasn't silent. The spacecraft was still transmitting, still sending its faint signal across 24 billion kilometers of space, still arriving at the antennas on Earth after its 22-hour journey. But the data it contained was gibberish, meaningless, a stream of ones and zeros that didn't resolve into anything interpretable, that matched no known pattern, that told the engineers nothing about what the spacecraft was actually doing or measuring. For 5 months, they didn't know why. The team tried everything. They sent commands across the 22-hour distance and waited 22 hours for each response. Each exchange, question and answer, took 44 hours of clock time. A conversation that might take a minute in person took nearly 2 days. In those 2 days, the universe continued to expand, the spacecraft continued to travel, and the engineers sat with their uncertainty and their 47-year-old equipment and tried to diagnose a problem 24 billion kilometers away. What they eventually determined was that one of Voyager 1's 3 onboard computers, a flight data system computer responsible for packaging and transmitting the spacecraft's data, had developed a problem with a small portion of its memory. Approximately 3% of the computer's total memory had become corrupted, likely due to a high-energy particle from interstellar space striking the chip and flipping a bit. The corrupted memory contained the code that formatted the data for transmission. When the computer tried to package the science data to send home, it was running partly broken code, and the result was the stream of nonsense that had been arriving at Earth for months. The fix, when the engineers figured it out, was ingenious. They could not repair the damaged memory. It was hardware, not software, and 24 billion kilometers away. But they could reroute. They could rewrite the code that the computer used to package the data, spreading it across different, undamaged sections of memory in a way that avoided the corrupted portion entirely. But here is the challenge. The code had to be sent across 24 billion kilometers of space. Every change had to be carefully written, carefully reviewed, and carefully transmitted, because if the transmission was wrong, if the new code introduced a new error, there was no guarantee they could fix it again. There was no guarantee Voyager 1 would survive a second crisis of this kind. The spacecraft was old. Its power was declining. Its systems had been running continuously for 47 years. They sent the fix in pieces over several weeks. Each piece traveled 22 hours to Voyager 1. Each response traveled 22 hours back. The engineers waited and checked and waited again. In April 2024, Voyager 1 sent back coherent data for the first time in 5 months. The team at JPL, engineers and scientists who had spent their careers listening to the spacecraft, some of whom had been on the mission for decades, described the moment as one of the most emotional in the history of the mission. Not because the science was particularly dramatic, though the science mattered, but because Voyager 1 was alive again, something they had built, something that had been traveling for 47 years, something that was farther from home than any object in human history, something that was, in a very real sense, irreplaceable. It had come back. Out there, right now, something is still happening to it. And the story of what Voyager is experiencing in interstellar space is stranger and more significant than most people realize. Right now, Voyager 1 is traveling through interstellar space at approximately 38,000 miles per hour, about 17 kilometers per second, relative to the Sun. In human terms, that sounds fast. It is fast by any everyday standard. At that speed, you could circle Earth in roughly 18 minutes. You could reach the Moon in about 7 hours. And yet, at that speed, crossing the distance to the nearest star system, Alpha Centauri, 4.37 light-years away, would take approximately 73,000 years. Voyager 1 is not heading toward Alpha Centauri. But even if it were, the crossing would take longer than all of recorded human history, multiplied many times over. Interstellar space is not empty in the way that everyday language suggests. It contains matter, thin, cold, electrically charged gas called plasma, at densities so low that they would qualify as a better vacuum than anything achievable in a laboratory on Earth. It contains cosmic rays, high-energy particles moving at close to the speed of light, originating from supernovae and other violent events throughout the galaxy. It contains magnetic fields, woven through the fabric of space by the movements of charged particles over billions of years. Voyager 1 is measuring all of this. Right now, in real time, the cosmic ray measurements are particularly significant. Every day, Voyager's instruments count the number of high-energy particles arriving from the galaxy. The data builds slowly into a picture of what the interstellar radiation environment actually looks like, not modeled, not theoretical, but measured. This matters for future human space travel. Any crewed mission beyond the solar system would expose its passengers to this radiation. Understanding it is not an abstract exercise. The temperature of the interstellar medium that Voyager is traveling through is strange. The plasma around the spacecraft is extraordinarily hot, tens of thousands of degrees, but the density is so low that the actual thermal energy present is minimal. If you were somehow present in that environment without a spacecraft, you would not feel warmth. You would feel cold. The temperature measurement reflects the energy of individual particles, not the density of them. In interstellar space, temperature and heat are not the same thing. The magnetic field measurements have been consistently surprising. The orientation of the interstellar magnetic field is different from what the models predicted. The field appears to be roughly aligned with the galactic plane, the plane of the Milky Way, but the detailed structure is not what the best theoretical work suggested it would be. Each discrepancy refines the models. Each refinement improves our understanding of the galaxy we live in. And Voyager 1 is doing this alone, in the dark, in silence, except for the faint hum of its instruments and the steady whisper of its transmitter, sending data home across a distance that grows by about 1.5 million kilometers every day. The Sun, from Voyager's position, is just another star. Bright, but not overwhelmingly so, brighter than any other star in the sky, but not the dominant feature of the heavens that it is from Earth. In every direction, stars. The Milky Way's disk visible as a band of concentrated light across the sky. The galaxy seen from outside its own spiral arm, beginning to resolve into structure. And nothing else. Nothing close. Nothing moving. The nearest star system still tens of thousands of years away at Voyager speed. The nearest human being 24 billion kilometers behind, listening. Every day, a signal leaves Voyager 1 and begins the longest routine journey of any signal sent by human technology. The transmitter that sends it produces 22.4 watts of power. That is less power than a standard household light bulb. It is the amount of power that a dim nightlight uses. And from 24 billion kilometers away, the 22.4 watt signal arrives at Earth with a power level of approximately 10 to the power of minus 16 watts. A number so small it is essentially meaningless in everyday terms. It is, by a significant margin, the weakest signal that human technology routinely detects. To receive it, NASA uses the Deep Space Network, a system of enormous radio antennas located at 3 sites around the world, chosen to provide continuous coverage of the sky as Earth rotates. The sites are in Goldstone, California, Madrid, Spain, and Canberra, Australia. The antennas at each site are massive. The largest are 70 meters in diameter, the size of a 20-story building laid on its side. They are pointed at Voyager 1 with extraordinary precision, tracking its position as the spacecraft moves and Earth rotates, maintaining the lock on the signal with a precision that is itself a remarkable engineering achievement. The signal travels from Voyager 1 to Earth at the speed of light. It takes 22 hours and some minutes to make the crossing, the exact time varying slightly as Voyager moves farther away. The engineers at JPL know where Voyager 1 is at any given moment to within a few kilometers, a precision achieved through careful measurement of the Doppler shift in the signal's frequency, which changes slightly as Voyager moves, and through years of careful tracking. When a command needs to be sent to Voyager 1, when the engineers need to adjust an instrument or upload a software patch or simply check a system, they send it from Earth and then wait 22 hours for the signal to arrive. Then whatever time the spacecraft takes to process and respond. Then 22 hours for the response to come back. A single exchange can take 2 days. A complex troubleshooting sequence can take weeks. The people who manage this communication have developed a patience that most people will never need. They think in timescales of hours and days rather than seconds and minutes. They write commands carefully, review them exhaustively, and then wait. The waiting is not frustrating for the most part. It is simply the nature of the work. You are talking to something 24 billion kilometers away. Takes time. You accept the time. There is something almost meditative about it. A kind of enforced slowness in a world that has become defined by immediacy. You send a message. You wait 44 hours for an answer. The universe does not hurry for anyone. And every day the signal comes. Faint, reliable, carrying its small cargo of data across the impossible distance. A machine built in 1977, running on the heat of decaying plutonium, transmitting its measurements of interstellar space to a planet it left nearly 5 decades ago. Every message it sends takes 22 hours to reach us. And one day, not long from now, in the context of the mission's total life, those messages will stop. And what happens then is something the people at JPL think about more than they publicly discuss. Voyager 1's power source is running out. The 3 radioisotope thermoelectric generators that have powered the spacecraft since 1977 produce electricity from the heat of decaying plutonium-238. Plutonium-238 has a half-life of 87.7 years, meaning that every 87.7 years, half of the remaining radioactive material has decayed and is no longer producing heat. The process is slow but inexorable. In 1977, the generators produced approximately 470 watts of electrical power. By 2024, that output had declined to roughly 310 watts. It continues to decline at a rate of about 4 watts per year. To compensate, the engineers have been shutting down systems on Voyager 1 over the years. Heaters, non-essential instruments, systems that were once considered necessary have been switched off, one by one, to preserve the power needed to keep the remaining instruments running and to keep the transmitter alive. Each shutdown is a small loss, a capability removed, a measurement that will no longer be made but necessary to extend the mission. The trajectory of the power decline points toward a specific ending. Sometime around 2025, the engineers will need to begin shutting down science instruments, the actual sensors that have been measuring interstellar space and sending back data. One by one, the eyes and ears of Voyager 1 will go dark, as the power available can no longer sustain them all. The spacecraft will still transmit, but it will have less and less to say. By around 2030, it is expected that the power will be insufficient to operate any science instrument reliably. The transmitter may still function, but it will have nothing to transmit except the carrier signal itself, a steady radio tone, saying nothing more than "I am here." And eventually, sometime in the 2030s, the power will drop below the level needed to maintain the transmitter. The carrier signal will weaken. The engineers will notice the change in the data they receive, a slight drop in signal strength, a degradation in quality. And then, one day, the signal will not come. Not dramatically, not with any announcement. The universe will not mark the moment. The signal will simply not arrive the way any signal eventually fails, not with a decisive end but with a slow fade into the background noise of the cosmos. The people at JPL will know it's coming. They will have been watching the power levels for years, making increasingly difficult decisions about which systems to sacrifice to extend the mission by months or weeks. They will have been listening more carefully as the signal weakens, as if paying closer attention could somehow delay the inevitable. And then it will be quiet. The most distant human-made object in existence will go silent. After nearly 6 decades of faithful transmission, after sending back data from Jupiter and Saturn and Titan and the heliopause in interstellar space, after surviving a near-fatal computer failure at 24 billion kilometers from home, after carrying a golden record with the sounds of Earth through the silence of the cosmos, Voyager 1 will stop talking. But it will not stop moving. That is perhaps the strangest part. One day, without warning, it will go quiet forever. But it will keep going, traveling through interstellar space at 38,000 miles per hour, long after the last signal has faded, long after the last person who worked on the mission has died, long after everything we know has changed. The golden record will still be there, still attached to the spacecraft, still carrying its cargo of human music and human voices and human hopes into a darkness that has never heard any of it. And in 40,000 years, something will happen. In approximately 40,000 years, Voyager 1 will make its closest approach to another star. The star is called Gliese 445. It is a red dwarf, a small, dim, cool star located currently about 17.6 light-years from Earth. It is not remarkable in itself. Red dwarfs are the most common type of star in the Milky Way, and Gliese 445 has nothing particularly special about it from a distance. But in 40,000 years, Gliese 445 will be approximately 1.6 light-years from the Sun, having moved closer due to its motion through the galaxy relative to our solar system. And Voyager 1, still traveling at 38,000 miles per hour, will pass within about 1.7 light-years of it. That is not close by interstellar standards. Voyager 1 will not enter the Gliese 445 system. It will not pass through any planetary system. It will pass in the neighborhood of the star, in the way that ships on different courses might pass in the neighborhood of the same island, close enough to note, not close enough to stop. In 40,000 years, it is almost certain that no one at JPL will be tracking Voyager 1. No one currently alive will be alive. The organizations that built and operated Voyager, NASA, JPL, may not exist in any form we would recognize. Human civilization in 40,000 years is essentially impossible to predict. The only thing that seems clear is that whatever humanity becomes in that time, it will be very different from what it is now. Voyager 1 will make its passage past Gliese 445 without anyone from Earth watching. No antenna will be tracking it. No signal will be received because the power to send one will have been gone for tens of thousands of years. The spacecraft will pass through its closest interstellar approach alone, in silence, carrying its golden record, and continue on into the galaxy. The question of who might find it is one that sits at the intersection of astronomy and probability and philosophy. The honest answer is that finding Voyager 1 without knowing where to look would be essentially impossible. Space is too large. The spacecraft is too small. Even if a civilization existed in the galaxy with technology far beyond ours, stumbling upon Voyager 1 by accident would require a coincidence so extraordinary that it approaches impossibility. But the golden record contains a map. The instructions on the jacket of the record include a diagram showing Earth's location relative to 14 pulsars, rapidly spinning neutron stars that emit regular pulses of radio energy with characteristic frequencies. Pulsars are like cosmic lighthouses. Their pulse frequencies are distinctive and stable, and a civilization with radio astronomy capability could use them as reference points to determine Earth's location from the map on the record's jacket. This means that if Voyager 1 is found by any means by any intelligence anywhere in the galaxy, the finder will know where it came from. They will have directions. Carl Sagan was aware of this when the record was designed. He considered it and decided that the benefit, the possibility of contact, of connection, of making our existence known to something beyond the solar system, outweighed the risk. He believed that a civilization advanced enough to find Voyager would be advanced enough that fear of contact was unwarranted. Others have been less certain. In the context of the Fermi paradox, in the universe of the dark forest hypothesis, where civilizations hide and any announcement of location is a risk, the golden record could be read differently. Not as a message of hope, but as a cosmic address, freely given to whoever happens to find it. But Sagan's optimism holds a kind of logic that is hard to argue with fully. If we are afraid to say we are here, then we have already decided that the universe is hostile. And if we have decided that, then the silence we hear from the cosmos becomes a mirror, reflecting back not the nature of the universe, but our own fear. The record is out there. The map is on it. Whatever happens next is not something any of us will live to see. There is a specific thought experiment that helps illuminate what the golden record actually is. Imagine that the sun expands, as it will in approximately 5 billion years, and engulfs the Earth. Everything on Earth, every building, every book, every hard drive, every piece of music ever recorded, every photograph ever taken, every word ever written, is destroyed, vaporized, gone. The only copy of any human cultural artifact that survives is the golden record on Voyager 1. This is not a fantasy. This is, as best as we can determine, literally true. In 5 billion years, when the sun becomes a red giant and the inner solar system is consumed, Voyager 1 will be in deep interstellar space, far enough from the sun that its destruction will be irrelevant to the spacecraft. The record will still be there, still intact, still carrying Bach and thunder and a mother's first words to her child. It is the only copy of humanity that will outlast the sun. That thought lands differently depending on who you are and when you encounter it. For some people, it is comforting, a kind of immortality, however thin, for the civilization that produced it. For others, it is melancholy, a reminder that everything else will be gone, that the golden record is all that will remain. Carl Sagan described it in terms of a message in a bottle. But a message in a bottle implies the hope of rescue, of contact, of a response. The golden record may never be found. Its cargo of human music and human voices may travel through the galaxy for billions of years without ever reaching any ear capable of receiving it. The most eloquent statement humanity has ever made about itself may disappear into the silence without leaving any impression on the universe. And yet it exists. It is there. It is real. There is a kind of stubborn dignity in that, in the choice to send it at all, in the choice to put blind Willie Johnson on a spacecraft and launch it into the dark, knowing the odds, knowing that knowing the odds doesn't really capture the scale of improbability involved, and doing it anyway. The golden record is not primarily a message for aliens. It is a message about us, about what we chose to preserve when we had to choose, about what we thought was beautiful and true and worth the effort of gold plating and encoding and sending into the void, about what we are when we are at our most deliberately consciously human. Every civilization, in whatever time it has, makes choices about what matters. The golden record is humanity's most explicit statement of those choices, sent beyond the solar system, beyond the reach of any future catastrophe, beyond the lifespan of the sun itself. One gold-plated copper disc, 12 inches in diameter, carried on a spacecraft the size of a compact car, traveling at 38,000 miles per hour through interstellar space, past the stars into the galaxy, for as long as the galaxy exists. That is what humanity sent into the dark when it had the chance. Voyager 1 is not alone in interstellar space. Voyager 2, its twin, its companion, launched 16 days before Voyager 1 on a different trajectory, is also out there, traveling in a different direction at a slightly slower speed, but also beyond the heliopause, also in interstellar space, also sending its faint signal home. Voyager 2 crossed the heliopause in November 2018, 6 years after Voyager 1. Its crossing happened at a different point on the heliopause surface, in a different direction from the sun. And the data it returned from its crossing was subtly but significantly different from what Voyager 1 had measured. This was important. With two spacecraft crossing the heliopause at different locations and different times, scientists could begin to understand the structure of the boundary itself. Was it uniform? Did it vary with location? Did it change over time? The comparison between the two crossings revealed that the heliopause is neither perfectly smooth nor perfectly static. It varies in thickness and properties depending on where you cross it. 2 data points instead of 1. 2 perspectives on the same boundary. 2 streams of data from 2 different directions in interstellar space, both traveling home across billions of kilometers, both being received and processed by the same network of antennas that has been listening since 1977. Voyager 2's journey to the heliopause was also scientifically richer than Voyager 1's in one specific way, because Voyager 2 took a different trajectory through the outer solar system, one that sent it past Uranus in 1986 and Neptune in 1989, neither of which Voyager 1 visited. It was the only spacecraft to ever fly past all 4 of the outer planets. At Uranus, Voyager 2 found a planet tilted almost completely on its side, rotating at an axial tilt of 98 degrees, meaning its poles point roughly toward the Sun rather than its equator. The cause of this extreme tilt is unknown, but is believed to be the result of a massive collision early in the solar system's history. The planet radiates almost no heat from its interior, unlike all the other giant planets, suggesting something unusual about its formation or internal structure. At Neptune, Voyager 2 found a world of extraordinary atmospheric activity. Winds in Neptune's upper atmosphere reach nearly 2,000 kilometers per hour, the fastest measured anywhere in the solar system. And orbiting Neptune, Voyager 2 found Triton, a moon that orbits in the opposite direction from Neptune's rotation, geologically active, with geysers of nitrogen gas erupting from its surface, and an orbit that is slowly decaying. In roughly 3.6 billion years, Triton will cross the Roche limit and be torn apart by Neptune's gravity, forming a ring system around the planet. Voyager 2 is also alive, also transmitting, also carrying a golden record. 2 spacecraft, 2 golden records, 2 messages from humanity traveling in different directions through the galaxy. Both still going, both still talking to Earth. It is alone too, but it went a different way. And together, the 2 Voyagers have given us more knowledge about the outer solar system and the space beyond it than any other mission in history, more, arguably, than all other missions combined. There is a photograph on the wall of the Mission Operations Room at the Jet Propulsion Laboratory in Pasadena, California. It shows the pale blue dot, Earth from 6 billion kilometers away, a fraction of a pixel in a beam of scattered sunlight. The most humbling photograph ever taken. Hanging on the wall of the room where the engineers come every day to listen to a spacecraft that took the photograph 34 years ago and has not stopped traveling since. They come in, they check the signal, they verify that Voyager 1 is still there, still transmitting, still sending its measurements of interstellar space home across 22 hours of empty space. And they do their work, processing the data, writing the commands, waiting for the responses in the company of that photograph. The Voyager mission has now been running for 47 years. The people who work on it today are, in many cases, the inheritors of a tradition rather than its originators. The engineers who built the spacecraft are mostly retired or gone. The scientists who first proposed the mission, who fought for the funding, who stayed up the night of the launch watching the rocket disappear into the Florida sky. Most of them have moved on or passed away. The mission has outlasted the people who started it, and it continues. There is something in that continuity that is worth sitting with. Something that says something about what human beings are capable of when they choose to be. A project begun in 1972, still running in 2024, spanning more than half a century, outlasting the technology that built it, the culture that funded it, the specific people who created it. Running on patience and institutional memory and the commitment of successive generations of engineers who chose to inherit this particular responsibility. Voyager 1 is, by any measure, the most remote object in human history. It is farther from Earth than anything we have ever built. It is in a place that no human being has been and that no human being will reach in any lifetime now being lived. It is alone in a way that no human being has ever been alone. Utterly, completely, without possibility of companionship or rescue or even the comfort of visible light from home. And it was made by people, designed and built and launched and listened to by people. People who got up in the morning and drove to work and drank their coffee and sat at desks and wrote code and calibrated instruments and did, on an ordinary Tuesday, the extraordinary thing of maintaining a conversation with the most distant object in human history. That is what the Voyager mission is. Not the spacecraft, not the data, not even the golden record. It is the conversation, the 47-year, unbroken conversation between humanity and its most distant creation. A conversation maintained through power fluctuations and computer failures and the slow dimming of a plutonium heat source and the passage of decades and the death of the people who started it. A conversation about what's out there, about what the solar wind feels like at its edge, about what interstellar space tastes like magnetically and electrically and in terms of high-energy particles, about what Jupiter's moons look like up close, about what a spinning storm the size of 3 Earths looks like in color, about what Titan's atmosphere is made of, about what the solar system looks like from the outside, all its planets arranged in the dark, one of them barely visible. A conversation that will end sometime in the 2030s, when the power finally fails and the transmitter goes quiet and the signal stops, arriving at the antennas in California and Spain and Australia. And then Voyager 1 will continue its journey in silence. Without us, without the conversation, carrying its golden record through a galaxy it will take millions of years to cross, past stars it will never be close enough to feel, through a darkness that has no edge it will ever reach. In 40,000 years, it will pass near a red dwarf star, and nothing will happen. In 300 million years, it will have completed roughly 1 orbit of the galaxy. The Earth it left, if Earth still exists, and it may not, depending on what happens in those hundreds of millions of years, will be unrecognizable. The continents will have moved. The species will have changed. The civilization, if there is one, will bear no recognizable relationship to the one that built the spacecraft. In billions of years, if the galaxy survives its eventual merger with Andromeda, Voyager 1 will still be moving, still carrying a golden record. Still, in some sense, a piece of us, the last durable artifact of a civilization that existed for some thousands of years on a small rocky planet around an ordinary star. What Voyager 1 is, in the end, is a choice. A choice made by people in 1977 to send something into the dark. To build it carefully, power it with plutonium so it would last, load it with a golden record so it would carry something of us, and aim it outward into the interstellar space that surrounds the solar system, into the galaxy, into whatever the universe holds. A choice made with full knowledge that it would travel beyond any ability to retrieve it, that it would go silent before it reached anything, that the golden record might never be found, that the pale blue dot it photographed would eventually be consumed by the expanding sun, and Voyager 1 would keep going anyway. They made that choice. They built the spacecraft. They launched it on a clear night in September 1977, and they have been listening to it every day since. Right now, as you listen to this, a signal is making its 22-hour journey toward Earth, carrying measurements of interstellar space, carrying the quiet testimony of a machine that has been alive in its way for 47 years, crossing a distance that grows by 1.5 million kilometers every day. It will arrive. The antennas will catch it. The engineers will process it. And Voyager 1 will be, for another day, still there, still alone in the dark, at the edge of the solar system and beyond, carrying music into a silence that has never heard any. Still going. Sleep well.